Hey, good morning. So what we're going to do today is we are going to continue our study of binary search trees. We are going to go over how to find the minimum and maximum value in a binary search tree, how to return specific pointers within a binary search tree. Then we're going to learn how to delete elements from a binary search tree. So one of the trade-offs when we were discussing this whole idea of why binary search trees as opposed to a hash table or as opposed to a singly or doubly linked list or a dynamic array is that we're allocating precisely as much memory as we need to. So with a hash table, we have to do lazy deletion in order to maintain our probing algorithms. With a doubly linked list, we have to search through a big O of n every single time. With a binary search tree, we're starting to see that as we do these decisions, that we can get we can get some big O of log n, and we'll memorize big O of log n search time. And so what I want to do is first review and go over in more detail what I was discussing at the end of last lecture was this level order traversal. So in the level order traversal, I asked you, how would we try to get it to return so we have the levels 15, 10, 25, 6, 12, and 30? And you correctly answered that that's pretty much the same thing as doing a breadth first search on a graph. And so that's exactly what it is. And in fact, if you did a breadth first search on a graph, you will produce a tree. And we also know from what we've learned that the data structure Q, we use that to be able to store a first in, first out data structure to keep track of which elements we need to evaluate. Also, with our understanding of void pointers, we now can point to the address of a specific location. And this becomes beneficial when using breadth first search, because if we were making a copy of the data in the binary search tree, it could potentially be prohibitive. In these examples that I'm showing you on the slides, it's integers or unsigned ints, something small. However, if we're doing databases with really large pieces of information that correlate to anybody, if we're storing pieces of information about a person, every single node is going to contain lots of information. And so if we make a copy, just to do for example, a level order traversal, we're using up a lot of memory that we don't need to. So we can accomplish the exact same thing by just pointing to the specific node. We can do it just as fast, and except we're even doing it slightly faster because we're not making copies of huge pieces of data every single time. No matter how big the data inside of the node, by using the pointer, we are able to perform this traversal in the exact same time. So it runs a little faster, but we get a potentially significant improvement in memory. All right, so does anybody have any questions before I go through the code? Let me check the chat. All right, so the code is on the left, and this is a print level order where I'm passing a O stream and a const binary search tree node where I'm passing the root. So if tree root is equal to null, then we just return. Now I create a queue of void pointers. Now I say level queue.push tree root. Now tree root is a BST node. So the difference here, as we've been learning this semester, is that a binary search tree node or any kind of pointer, like the binary search tree node pointer, or an int pointer, or a char pointer, is pointing to a location in memory and telling the operating system to interpret it as some sort of chunk of data, right? So here what I'm doing when I cast to void star tree root is I'm saying, all right, I have that base address, but in order to be able to perform everything else, that's all I need. I don't need anything else. Just give me where it starts, and then I'll write code later to be able to cast it back. So now what I'm doing here is I'm performing this, but reducing the memory I need in order to perform the level order traversal. So just like before, when we did the breadth first search, we kept going while this queue is not empty. So this will allow us to be able to evaluate every possible node. You may also notice that since we're doing it with a BST, remember when we did it with graphs and I had this visited Boolean array? And the reason we had to do that is there could be the potential of this coming back. In a binary search tree, because we've set up the insertions a specific way, there will be no loopbacks. So as a result, you're going to see that there is no Boolean dynamic array that contains all the potential locations. What I do instead is I say that the BST node cur node pointer is going to be equal to, I take the void pointer at the front of the queue, I cast it to a BST node pointer, and then I create that current node. So then what I do is I pop it off, and then I print it out, because ultimately what we're trying to do is we're just printing out the level over traversal. So then I do this. Now notice how it's not recursive. What I'm doing is I'm getting the left and the right, and I'm pushing them onto the queue. So I'm getting the current node left's void pointer and current node right's void pointer. And also note that I'm doing it when they're not null. So let's walk through the animation and see what happens. So first, I put void star 0, and I push in, I'm casting to void pointer, and then I say, well, it's not empty. So then what I do is I say, BST cur node is currently pointing to the node containing the value 15. So I've now cast it back, and then I remove level from the queue. I print out 15, and then if cur node left is not null, then I'm going to get a void pointer to 10. Does everybody see that? And then I check right as well, and then I get 25. And that's how we're able to maintain the level order. So then I go up, it's not empty. We see that void star 1 is in the front of the queue, so that's going to be 10. Then I remove that from the queue, and then I would print out 10. And then if cur node, which is currently pointing at 10, is not null, then I'm going to push the pointer to the left, which is the node containing the value 6. And then I'm going to do the same thing with the right, which is going to be a void pointer pointing to the base address of the node containing the value 12. So now I go to the front again, it's void star 2, so that's going to be the one containing 25. I remove that from the queue, and then 25's left pointer is null, so we don't put anything in. And then 25's right child is not null, so we push void star 5, which is the node containing 30, onto the queue. So then 3, put in 6, both of its children are null. Then I go to void star 4, it's 12, both of its children are null. And then void star 5 is the one containing 30, and both of its children are null. And now the queue is empty, and we have completed the level order traversal. And so when I print out this particular tree with make test BST5, what we'll see is it now prints out the in order, the pre-order, the post-order, and the level order traversals. So this tells us everything we need to know. If you know all this information, you can create any tree in any order. All right, the next thing I'd like to show you is how do we know if a specific data is in our binary search tree? So now we're going to just take advantage of what we've been learning in the last couple lectures and break this into public and private recursive calls. So a couple weeks ago, one of you, and I apologize, I can't remember who, asked me, when is it a good idea to break it down into a public and private recursive call? So the public, all I'm doing is I just want the user to be able to insert data that they want to search for. And all they need to know is if it's in there or not, right? So we have abstraction. We've abstracted a lot of this complexity away from the program. Then we have a private member, or a private method, that is going to pass the private member root. So by separating these out, the programmer is not accessing the private member root. And then here, what I'm doing is I pass curve pointer in the element. And the first thing I do is, if I've got all the way down to the bottom of the tree and doing these choices, if I reach a null pointer, that means the value is not in the tree and I return false. If the current data is equal to the element, then it's equal to true, because we found it. Otherwise, what I'm going to do is I'm going to say, if the element is less than the current data, then I want to go down the left side of the tree. So I'm going to call contains again recursively with the left pointer. And otherwise, we have one last potential case where the element is greater than the current node, which means we go right, and then we recursively call curve pointer right. Does that make sense? findMin. findMin, I'm now not even worrying about right recursion, because the minimum element in the tree is the leftmost element. And so let me draw up a tree for you here. So let's say I have 10, 7, 8, and 12. Intuitively, we can look at this tree and we know that the smallest element is 7, right? The reason we know this is because 7 is the leftmost element in the tree. I don't have anything here that's null. So what I just do is I keep going left until I can't go left anymore. So again, we've split it up, public and private. Now I'm accessing the root. And I say if the curve pointer is equal to null, return curve pointer. Otherwise, if curve left is equal to null, return curve pointer. And then findMin curve pointer left. So here's what these two pieces of if statements are doing. If I first check and there's nothing in the tree, I want to return the null pointer, right? Otherwise, what's going to happen is there has to be a case where there's at least one valid node. So therefore, if I go left and I check to see if the left pointer is null, then therefore I want to return the pointer to the current node. Does that make sense? This allows us to be able to return that location, and what we're doing here is we're returning the pointer, not the value. And this is going to become valuable to us when we perform other tasks. On Monday, I'm going to go over 4 different lead code interview questions that are pretty common about binary search trees, and we're going to see that our ability to access these pointers is going to make solving these problems significantly easier. findMax is the opposite. We just keep going right until we can't go anymore. So either return null, which is what we would do in the case of an empty tree, or when we return a value, that means we have found the largest element in the binary search tree. So for make test BST6, what I've done is I have first created a tree here with an in order, pre-order, post-order, and level order traversal. Then I test to see whether or not there are certain elements in the tree. So does it contain 12? It's 1, so in that case it's true. And we see that it does in fact contain 12. 12, 25. I've tested to see if 40 is in there. And if we look at these elements in the in order traversal, we see that 40 is not in the tree. 30 is in the tree, negative 30 isn't, 15 is. And so our max value, minimum value should also be the first element in the in order traversal. I know intuitively that makes sense, but if you've written up a proper binary search tree or a proper tree, that's what should come out. And we see that we have made the computer actually do this. And then the maximum value should be the first element in the post order traversal. Because think of it this way, findMin, we are just going down to the first element just like we do in the pre-order, in the in order traversal, right? And then in findMax, we're basically going down to the right, just like we're doing in the post-order traversal. And we see that max value is 30. Okay, so we have a question in the chat. And Livia asks, how do we know what the root is in the public methods? So the root in the binary search tree is a private member. All right, a lot of code here. Okay, so we have a private member of the class BST node root. And whenever we create and insert our first element, that is going to be the pointer to the root. So it's going to be one of two things. Either it's going to be null, in which case we have an empty tree, or it's going to point at the first element. So let's say I insert 10, 25, 17, and 6, right? So I would insert 10, and that root is going to be pointing at 10, at which point I would insert 25, 17, and 6. So root is going to return the pointer to the node containing 10. So Olivia, did that address your question? All right, awesome. All right, so let's continue. Now, one thing I have here in the animation is that you'll notice they say the tree.findMin, it returns a pointer. So what we are able to do in C++ is we use minus sign greater than to represent an arrow. The other way you would have to do this is if you had to do star the tree.findMin and then dot data. So this is a little clearer as to how and why you can do that. But basically, that's just dereferencing a pointer that is passed to us, and then the dot data allows us to be able to access the member of the node BST node struct. All right, so the next thing I would like to discuss with you is how to delete from a binary search tree. So up to this point, we've learned insertion, in order, pre-order, post-order, level order, how to find something, findMin, findMax, and contains. So if I want to delete certain elements from the tree, I want to ensure that I can perform all of those tasks. The issue is if I don't properly allocate the pointers, then it becomes a problem. So if I want to delete 10, well, 15 has to point somewhere, right? We could theoretically do this. We could say 15, 12, 6. Does everybody see that? Or if I said I'm going to choose the max, but I could also do this. I could also do 15, 6, 12, 25, and 30. So when I do that, what that allows me to do is I say I'm still maintaining the order of the tree. I still know that if I did findMin, I'd still come up with 6, correct? If I did findMax, I'd still come up with 30. And if I did find contains 12, we'd still be able to find it. Both of those trees that I put up there worked. So ultimately, it comes down to a design choice. And what you're going to see is that most binary search trees that you encounter pick the maximum value to bring up. Now, if I just delete it, if I were to just delete the node, then we would lose track of everything. So this slide just basically says exactly all the things I was just talking about. Okay, so to find the element, first we're going to recurse down the tree. And then if we were just looking for contains, we just return the location. So if we return null, that means the element that was requested to delete is not in the tree. And when an element is deleted, we know that the node pointer is pointing to that node, so we found a specific thing, right? and that node has 2 children. We also know that either of them may be null. Both may be valid children, both may be a null child, one may be. So we have to consider all 3 of these scenarios. And so what I would like to do is I first want to show you I'm going to quickly show you the public remove here, and then I'm going to go to the BST node, BST code, and show you the private so I can zoom in and show you in more detail. So here I am requesting an element, and in the public method, what I'm doing is I'm just removing, I'm starting at the root, and I'm continuing with recursively to pass that element. Does that make sense so far? All right, so ignore the virtual. That's going to be something we're going to cover later in lecture. So with the remove, notice how when I'm passing the cur pointer, that I'm calling it by reference. It's because when I delete something, I want to make sure that when we propagate it back up, that those changes are preserved. First things first, if we hit a null pointer, that means we've traversed everything and we haven't found the element in the tree. So now I have to consider all these scenarios. First, if the element is less than the current data, I want to recursively call remove with a cur pointer to the left. Likewise, if cur element is greater than the cur data, I want to remove the element to the right. I mean, we're going to remove recursively by calling the right pointer and going recursively to the right. So now I have to consider these 3 scenarios. We are now at the point where I'm at the node, we have found the data, we are deleting. The first case is if the parent has 2 children. Now remember I mentioned this on Wednesday, how when we're doing trees that you're going to see over and over again that I'm going to constantly check for non-null pointers. So for those of you who were on the lecture, on the optional lecture last night, that was something that I hit on really hard over and over again. Max path sum, we got to check for null pointers. Subset of another tree, we got to check for null pointers. This is another example. Here, if you don't do this and you check the values of them and one of them is null, you will segfault. So here, what I'm doing is I'm first saying, all right, I want to check these values, but I have to check to make sure that they're not null. Here, what I've done is I set the current node's data to the minimum value, and I pass cur data right to get the minimum to the right. So let's say I have 10, 6, 15, 13. If I have 2 children, what I'm doing is I'm finding the minimum, right, of the right child. So the minimum here will go to 13. Everybody see that? And now what I'm doing here is cur pointer data is going to be equal to that data value. So now what I'm doing is I'm saying, all right, instead of 10, this is now 13. Does everybody see that? That's what that code's doing. And then I'm actually going to continue to call remove. And then I say cur pointer right and cur pointer data. So what I have is I have 2 values, right? And so when I say cur pointer right, that's, I'm going this way. And now I'm looking in the subtree on the right for 13 because cur pointer data has been overwritten. And the reason I'm doing this is now we have a duplicate value, so we're going to recursively delete the duplicate. Does everybody see that? Right, else, there's only 1 child. So in this last case, I'm accounting for whether we have 1 null pointer or another. So what we're going to do is here, we're going to create a temp node, curve pointer, the temp is equal to curve pointer. And you're going to recognize this technique from doubly linked lists. So we set the curve pointer equal to the non-null child. So curve pointer is equal to, we do our evaluation if the left pointer is not null, then we set the curve pointer equal to left, otherwise we set it to right. And what that means is, let's say I have 13 and 15 here. I check to see if the left pointer is not null. In this case, it's not. And what's going on here is that curve pointer is here, correct? So whatever 13's parent is, whether it's root or it's another value, what I'm going to do is I am going to say, well, curve pointer is now pointing at 15. And I still have this temp pointer that's pointing there. And then what's going to happen is then I call delete temp. And just like we saw with the doubly linked list, temp now disappears. We have freed the memory for the node that we wish to delete, and we have maintained the integrity of the data. Likewise, if we do it the other way around, the way this would set up was we'd have curve pointer, and then we'd have 15, and let's say we have 10. First, I check to see if, first I say temp is equal to curve pointer, right? So we have temp, I'll put this over here, temp. And then I say if curve pointer left is not null, then we're going to say curve pointer is now pointing to curve pointer left. And then I free temp, which means we're going to free 15. So now all those pointers are gone. We've maintained the integrity. 10 is still in the tree, and we've done it correctly. And so with all these scenarios, we can replace min. That's something that's basically a design choice. We can also replace max. I've shown you both of those. And then here I show you the case for if it's left and if it's right. Then I would replace. Here I'm trying to delete 10 from the tree. So what I do is I move 12 up, and then I recursively call right. And then we have the case that I've just discussed where we have one child. And so what's going on here in this tree for test BST7 is that I have 15, 10, 6, 25, 30, and 12. So that creates the tree that's on the right. I do all of the tests. And then what I'm going to do is I'm going to call a function here, test remove. And what's going to happen in test remove is I'm going to call the tree by reference. I'm going to pass a specific value, and then I'm going to print the remaining tree afterwards. And so if my algorithm works correctly, then what's going to happen is it should remove elements and print a valid tree if the element was in the tree, and if not, it should print the exact same tree and tell me it wasn't there. And so let's run this. Clear, make test BST7. We're going to go all the way up here. All right, so here's their initial tree. I do all the contains. We have maximum value and minimum value. Deleting 25. Now 25 was initially in the tree, and we see that we have successfully deleted it. 12. Before we had 6, now we have 5 elements. We successfully deleted 12, so now we have 4. Deleting 15. 15 was in the tree, so now we have 3 elements here. Deleting negative 30. Negative 30 is not in the tree. Then we delete 30, which is in the tree, and we see that our traversal worked properly. We did not inadvertently misallocate any pointers, so we still have 2 elements in the tree. We delete 6, that takes us down to 1 node left, and then we delete 10. All of our elements are empty, so we now also know that our in-order traversal, pre-order, post-order, and level order all work appropriately, even for an empty tree. And then I tried deleting a 10 again from an empty tree, and it says that's not there. Right. So does anybody have any questions on BS tree, binary search tree deletion? Okay, so next thing I would like to do, all right, so then I actually go through this animation where I'm actually deleting all the elements in the exact order, so you can compare them on your own and see that we have the level order, pre-order, post-order properly maintained. The next thing I want to do is go over an advanced problem called max height. And so this one is a good one because it helps drive a lot of the things that we're going to be doing for the rest of the semester with trees. So in this problem, what we're going to do is we're just say, what is the maximum height of the tree? And the maximum height is defined as the number of nodes from the root to what we're going to call the deepest leaf. And in this example, 15 is the root, so that's 1, 10, 6, and 5. And so we're going to define this maximum height as 4. Does everybody see that? So the question is, how can, given a tree, any old tree, can we determine this maximum height? And so let me first, I'm going to show you the I'll first show you the public method first. So to reinforce this idea, all the user needs to do is ask what the maximum height is. Then what we're going to do is we're going to do a private call. We're going to pass the root pointer. And so now let's take a look at the private method. There we go. All right, so now we're at the private method for max height. And now what I'm going to do is if we have a null pointer, the tree is empty, we define that as 0. So that's what we're going to define for our recursive case. And that's what's going on here. When we say cur pointer equals null, then return 0 gives us a empty tree. And any subtree where we hit a leaf, that should be our a tree that is also 0. So this is a good way to start. Plus we're also testing to make sure that we avoid null pointers. Actually, I don't need to zoom out quite yet. Okay, so the next thing I want to do is I want to recursively check left and recursively check right. So I'm going to have a choice to make at every level. So for example, if I have 10, 7, 8, and 12, I have to make decisions at every level. So here, this is a null pointer. So this is 0 and 1. Does everybody see that? And then I add 1, so this becomes 2. 12 has 0 and 0. This becomes 1. And then 10 will make a decision between 2 and 1, and then we'll say 3. So now I know the max height. And so the last thing I've done is I've done another ternary operator. And so what I'd like to do is I'd like to walk through each piece of this line of code. So the first thing I do is I say, well, if max left is greater than or equal to max height of right, then I'm going to take the max height of the left. Otherwise, I'm going to take the max height of the right. And we can say greater than or equal to because since we're just returning the value, if we have a tie, it doesn't matter. And then, in order to move up 1, I'm going to add 1 level. So initially, if both of the children are null, I will recursively call it, it will return 0. I'll recursively call the other pointer, it will return 0. And then myself is 1. So if we have a node with a tree with 1 node in it, that's how we will know that we're getting the right value. Otherwise, it will return, just as I showed you in the drawing that I just did, that we can account for one or the other being larger to get the specific result. And so what I want to do is kind of just walk through that in an animation form. And it's not null, I check left. And here I say 0 on the left, I check right, I check 0 on the right. And then I add 1, and then I move up to 6. 6 is right child, is 0. So now 1 is greater than 0, so that gives us 2. And then here we have 0, 0, 1, 2 and 1. 2 is greater than 1, so now we have 3. And then we do the whole thing, the same thing with the right. So we have 0, 0 and 0, we get 1. 1 is greater than 0, 1 plus 1 is 2. So now we have 3 on the left and 2 on the right. 3 is greater than 2, 3 plus 1 is going to be 4. And so now we have proven that we can come up with the correct result on this. Yes? A tree with one node, at, like, so if it was 15 only, it would be 1. So there is a little bit of confusion if you like go online and look at resources. So what I'm defining this as a height, when I say nodes, I'm differentiating between node and node pointer. So if we said if the height was the number of node pointers, right? We'd have to go through root, which would be 1. Then we'd have to go through this pointer, which is 2, then 3, and then 4. We also get to 5 before we hit the leaf. So there's different ways of defining it. In this particular problem, I'm defining specifically for educational purposes, I'm saying, all right, let's go through the number of nodes to get through the actual height. So in this problem, the way I define it, a binary tree will have a valid root pointer. But if there's no node in it, it is not pointing to anything. So by my definition here, it will be 0. Did I clarify? Awesome. Let me check to see if there's any questions in the chat. We do not have anything there. All right, so this particular concept leads to a number of issues with a binary search tree. So let's consider this tree. I have 15, and remember when I was talking about this idea of asymptotic analysis, and the reason why I want to do asymptotic analysis is because we have to account for when the programmer doesn't do something that we were hoping they were going to do. They just keep doing something very silly. I say, well, I have a binary search tree, and this thing should give me big O log n search time, right? And this will allow you, if you don't know that what the sorted order is, you can store it. And then the customer goes, that's cool. I'm just going to put in a sorted order. Uh-oh. Now we basically have a glorified doubly linked list. Except we can't go backwards because all of the right children are null. So if we did it this way, what ends up happening is we get all the drawbacks of the doubly linked list and all the drawbacks of the singly linked list without any of our benefit of big O log n search time. So the whole idea is, well, how do I actually balance this tree? And so there are several ways to do this. There are several approaches. And what I'm going to show you for this lecture is the very first one that was designed in 1962 called an AVL tree. And so the reason why I want to show you an AVL tree is because it takes this idea of tree height and at every single opportunity goes, well, I want to make sure that I don't have one side that's more than one worse than the other at any given place in the tree. So it's formally defined in the rule, the height of a subtree of the left cannot be more than 1 greater than the height of the right subtree. So as a result, we're going to apply it the same way. We have to make sure that it's well balanced. So here we have 15 and 25. This is okay because the height of the left subtree of 15 is 0, and the height of the right subtree is 1. And getting back to your question about the definition, this is why I've picked this for lecture, because this helps the students identify better when to do balancing on trees. So then I put in 35. The height of the right subtree is 2, and the height of the left subtree is 0. So what we're going to do is we're going to start designing rotations. And what I mean by a rotation is, if we have an imbalance, we're going to want to rotate the tree. And so what's going to happen is we're going to say 0, 1. And now I've broken our rule. And so now I'm going to say, well, I'm going to say 25, the right child, is going to become the temporary root. I'm going to make 25's left child equal to the previous node. And that is going to allow me to rotate everything. And so here is the rule. We have to account for the children for A and B, and I want to rotate left. I'm currently pointing at A, and I've realized that my right subchild is greater than 1 in balance. So here what I'm going to do is I'm going to say, I'm going to create pointers to the parent and the child, and then I'm going to say that A's right subchild is going to point to the left subchild of the child. Do we see that? So before we were here at A, parent's right subchild is now going to point to the left child of B, like so. And so in this scenario, it should be like 10, 15, and 12. And if I'm moving this over, what's eventually going to happen, curve pointer is going to point at B, then I'm going to say that 10, his right child is going to be 12, and then I'm eventually going to say, well, 15's left child is going to be 10, which will then give us 15, 10, and 12. So we've maintained the ordering of the tree. So you'll see that the left child of B will become A. It'll point to parent. And then if we make it look, we'll move current pointer over to B. And if we clean this all up, this is what the new tree will look like. And likewise, we do it in the opposite direction. If we're rotating right, meaning that the left tree has broken the rule, then we're going to create the 2 pointers. We're going to say that A's left child is now going to point to B's right child, which is Y. And then what we're going to do is we're going to say that B's right child is now going to point to A, so it's pointing to parent. Then we're going to move curve pointer to point at the child, like so. Does everybody see that? And then if we clean it up, all that looks like that. So before I go dig into code, I just want to check to see if any questions are in the chat. All right, so for BST7 to BST.H, what I'm going to do is we're going to build an AVL tree, but I'm also going to reinforce inheritance and polymorphism, because most of the operations, insert and findMin, findMax, all these things that we have in there are the same. So I don't want to do too much extra work. So what I'm going to do in BST is that you'll see, first let me go to the constructor. You'll see that I have a virtual destructor, just like we should be doing for our inheritance and polymorphism. I have virtual void insert because I'm going to modify the insert method, but notice how the copy constructor, the assignment operator, contains, findMin, findMax, and remove are untouched. And then I have a private insert in BST that I've changed virtual because we're going to overwrite that as well. So in AVL tree 1.h, you'll see that I've included BST.h. In AVL tree, I've made it as a derived class of the binary search tree. Also, the binary search tree node is the same, so I don't even have to create a new AVL tree node. So we've saved ourselves a lot of work that way. So first I want to show you the insert method. And then in this insert method, I'm doing the same thing, but then I'm calling the private method. So this is why I have to overwrite that with virtual. With virtual, what I need to do is check rotate, check rotate. All right, so insert, I'm calling by reference. I'm doing the same thing as before where I'm doing the left and right recursions. And then I have this new method that I'm calling called check rotate. So in check rotate is up here. And so let me go through each of these methods in detail. Check rotate. First, I get the max height of the left subtree, and then I get the max height of the right subtree. That's what's going on here at lines 14 and 15. And that allows me to be able to perform my check. So if the left height is greater than the right by 2 or more, we're going to call rotate right. And then if right is greater than or equal to left height plus 1, we're going to call rotate left. For rotate left, now I'm going to do everything that I have in the animation. I'm going to create pointers, temporary pointers to parent and right child. And then I'm going to set the right child of the parent pointer equal to the left child of the child pointer, just like we saw in the animation. And then left child is now going to become pointing to the original parent. And then the last thing, I'm calling that parent by reference. So I set parent equal to child pointer. So that's that last step where we updated the pointer. Same thing in rotate left. It's just the same thing, but in the opposite direction. So I call the pointers again. Then I say parent pointer left is equal to child pointer right. Then I set child pointers right equal to the parent. So now that once I move this over in the last line at line 63, I now have the original left child as the new parent. And so when I run that, so here's all the code that I just showed you. Inheritance and polymorphism. Remember this root, that's why I had to do that, because we need inheritance and polymorphism there. I showed you rotate left and rotate right. I've shown you check rotate. I've shown you the insert method as well. And then, all right, I'll show you remove in a moment. I'll get to the, actually, no, I'll show you remove now. So in remove, what I've done is I have remove, and I'm doing the exact same thing initially as we did before with remove. We have element is less than cur data. I said was deleted equal to bool if I was able to delete it from the left tree. Likewise, I'm going to call remove from the right tree was deleted. And then else, now we're starting to break down all those cases again. Cur left does not equal null. Cur right does not equal null. This is just the same thing as we wrote before, but with this pointers, so we can use inheritance and polymorphism. And then else, this is that last case where we had either one child or the other child was null, but not both. And then the last thing is if cur pointer is not equal to null, I check rotate on the current pointer. So now we're doing that same thing. We're performing the checks. And so when I do test AVL, we see that I put in 15. We see now level order is 15 and 10. I now put in 6, so 6 is to the left of 10 normally, but then I will perform the rotate. So what we're going to see is we're going to see level order. Sorry. 6, and then I perform a rotation. See how we rotated left? And then my level order is 10, 6, and 15. So we see that the AVL tree is properly balancing. So I do 25, I add in 30, and again, we rotate. So what's happening here is the balance is broken here at 2 and 0. So it rotates, and we're going to see that 10, 6, 25, 15, and 30 is the new balanced AVL tree. And so if I insert again with 12, we're going to see here, so here we have 0, 0, 1, 0, 2, 1, 1, and 3. See how we have a violation? So now we need to rotate. And so what we're going to discuss in next lecture is that we performed a rotation, but we still haven't met our balance. So we have another thing we need to consider, and ignore that comment about max and min heaps. I apologize, we need to take that out. We're going to learn that a little later. But what we're going to do is we're going to investigate how to dig into more detail about these. So this will help you perform balancing on AVL trees. But also what this is going to allude to, and this is a good note to leave you on and dismiss, is that a lot of these balancing mechanisms are quite complicated. So with AVL trees, they tend to take the most time because we have to do a recursive call for max and min every single time. Then we have to do a rotation, and what you're going to see is we're going to have to perform another check, which means that we lose a lot of the benefit. So AVL trees are perfectly balanced, but what's going to happen is we're going to see that maybe not a perfect balance will actually improve the performance of our data structure. All right, so does anybody have any questions on this before I dismiss? All right, well then I will see you all on Monday. Have a wonderful weekend. Hey, we have a question in the chat. Is it possible to balance a BST by storing its in-order traversal as a list and then inserting the element in the middle of the list? So, okay, so basically you would be coming in, you perform an in-order traversal. Yeah, you would get, that's what I was about to point out. So the issue would be the big O of n to get the balance. And the problem is you have to do that for every single insertion. And what you will find is that when you, for trees, when you have a significant amount of stuff with databases, when you have thousands, if not millions of elements, that would become a pretty prohibitive. Okay, so Gavin, did that address your question? All right, well, you all have a good weekend. I'll get this uploaded in a moment.